So now, then we went to predict table. We know which group are the group for the semiconductor. The most important group are the group 3 and group 4, which is silicon is over here, germanium, and also group 3 and 5. Okay. Then I will go very fast. This is just a recap. So we have different types of material, conductor, insulator, and semiconductor. Should know the difference between them and also how the band gap looks like. And this is a very important graph of band gap versus lattice constant. You have the band gap and the y-axis and lattice constant, the x. And this maps what are the materials you can use to make sure that they are lattice match, right? So that you don't have defects. So this is very important. This normally always comes in the final exam also. And you know the color here, it means that if it's a direct band gap material, it will give out this color. Okay. And then what is this? Conduction band. Also, we went through very basic on what is conduction, what is intrinsic semiconductor, and how do you get carriers inside intrinsic semiconductor? You should remember, right? So it's due to the electron being excited from the valence band to conduction band, and vice versa for the holes from the conduction to the valence. Okay, at 0 Kelvin, you shouldn't have any current because there's no electron that can be able to go to the to the conduction band. There's no energy. And this is a graph of the intrinsic carrier concentration versus the inverse of temperature. So I asked you before to learn on your own, right? So you need to learn on your own. But normal mistake that students do, they you know, this is a graph. The y-axis is the intrinsic carrier density. The x, the bottom is 1 over t, 1000 over t. It's not t. Okay, so students normally got that confused. If you want to know, because we normally think with temperature instead of inverse of temperature, so you can look at the top here, it's versus temperature. So it's you can see on the it gets smaller to the right. So that's how you interpret. Okay, then doping. Should know what is doping, how do we dope, why do we dope? Why do we dope? Anybody can answer me? Why do we dope?
Get the required carrier concentration of holes or electrons as majority.
Again?
To get a required carrier concentration of holes or electrons, whatever we want, as the majority carriers.
Again?
To get a semiconductor of our own choice, for example, if we want a p-type semiconductor, we will dope it with a trivalent.
What's the main reason why we do?
To change the lattice constant?
No, you cannot change the lattice constant. Lattice constant is the arrangement between one atom, original atom to the other. So it won't change with doping. Okay, who else want to try? I cannot hear you, Tamana. Cannot hear you. I think the internet.
To control the electronic and electrical properties of the semiconductor.
Okay, that is the most important thing. Okay, why we dope is for us to control. We engineers, we like to control, right? If we cannot control anything, we cannot do anything. So the first thing is to understand, second is to control. Then we can design. If we know but you cannot control, there's no point. We cannot design anything, we cannot develop anything. So what we want to do is we want to control the conductivity or the resistivity of the material. Once we can control, we can make what do you call it, many things out of it. Okay, so that's the reason of doping. Okay, so you want to change the conductivity of the material, okay, so that you can make it into device. Okay, then we have so doping. Well, once you dope, it's called extended semiconductor. So you need to know what are the material to be doped. For silicon, at least you need to memorize. I will give you. So you need to know in order to become P-type, what material, to become N-type, what material. That's at least you need to know. Because if you go for interview, they will ask and you don't know, wow. They will say, what do you learn? So at least you need to know about silicon. The gallium arsenide or the rest is different material to dope. That's fine. I can give you table for that. But at least for silicon, you should know. If you want for it to become what do you call it, P-type, what should you dope it with to make it P?
Like arsenic.
So P, you need to have a material with only from group
Three
3.
valence electrons.
3.
3, yes.
3.
Kat mana sini? Tak ada kat sini lagi. It's not there yet. So this it becomes N, right? So this is group 5. If you silicon, you dope it with arsenic or phosphorus, you become group 5. If you want to become P, you dope it with I think boron.
Yes, ma'am.
So you need to know, at least here they give you arsenic or phosphorus, so you can memorize either one. Okay. Okay, so you need to know what's the effect of temperature to the carrier concentration, right? So we already gone through this. I won't repeat. Okay, so if you don't remember, make sure you go back to your notes. I assume you know. It's because we went through very slowly. Then we talk about energy levels. You need to know what are energy levels. Where are the energy levels? Can you have energy levels in the, what do you call it, in the forbidden band gap? Can you have energy levels inside the forbidden band gap?
Yes, ma'am.
Kamana say yes. Iman? Everybody has to answer. I only have 4 students.
Forbidden. Forbidden band gap.
Band gap. You know, band gaps, sometimes people will call it forbidden band gap. It's the same thing.
Oh,
I see. Can you repeat the question again?
Okay, my question, can we have energy levels inside the forbidden band gap?
yes.
Yes. Would.
Iman say yes, Ana say yes. Alam?
Yes.
Yes. Okay, answer why yes, Alam. You are guessing. Do you still remember anything about semiconductor device? I wonder, all of you. Yeah, I will die like this. I hope you still remember, because we're going to more advanced after this. We talk about mobility and scattering. If you don't remember this, no hope. So, Iman, why yes?
Wait.
The name is forbidden band gap.
Now I want to change my answer to no as I think about it, because the band gap is basically a gap between 2 levels where you need energy to cross the gap.
Yes.
From production band to valence band. So whether or not I wouldn't think there would be energy inside the gap in that case, since you need energy to cross. I don't know.
Okay, so you change to no. Okay, Anas, you, why yes?
Question is whether level, right? Not whether it can have energy level inside the energy band gap, is it?
Can you repeat? It's not clear.
The question, whether it can have energy level inside the energy band gap, is it?
Yes. And my question is, can you have any levels inside the forbidden band gap?
The
Energy
answer,
level or energy?
Energy levels.
Fermi,
You know what's the
Fermi,
difference? Huh?
the answer should be yes, because between the gap there is level. At certain level, uh, such as example the Fermi level,
Yeah.
there is a balance between them, right? And then
Fermi level is not energy level. It's just a level of to show the probability to find free carriers. Okay. So
to answer the answer is yes, because at there is certain level where the electron able to excite. The same with the hole.
yes, but you know, okay. Why the name forbidden band gap?
I don't know.
Okay, who wants to answer that?
Ma'am,
Yes.
maybe.
Okay, sure. Tawana?
Maybe because pure semiconductor will not have any levels there, but after doping it can have acceptor or donor levels in the forbidden gap.
Okay, the name forbidden because when we went through right before how do we form the balance band and conduction band. It's starting from, okay, I taught you before, but let me sketch. Stop sharing here and then okay. How do I share? Okay, can you see my iPad? Yes.
Yes,
Now,
ma'am.
Yes.
so remember last time we talked about the atom. So each atom has its own what do you call this ring?
Or
Orbitals,
atomic
right?
levels,
Orbitals.
orbit.
So each
Yes.
atoms have orbitals, right? So in one material, how many atoms you have? Do you know? Like millions or billions, right? In one
Millions.
square is you have a lot of atoms. So these atoms will interact. So these atoms, I change the color, will interact with each other. So this will interact with that, this will interact with that. And what happens is when these interact with each other, you will you can go and read about Pauli exclusion principle. If you Google this, there's a lot of YouTube on that. So this principle says that if you have a lot of atoms close packed together, what happens is all the orbitals, the energy levels will interact. Each of the orbital here is an energy level. Okay, so it will interact with each other because it's very packed. So what happens is it becomes it becomes in the end they will have two bands. It will become separated because of this principle. You have two bands. The top is called the conduction band and the bottom is the valence band. Valence band where you have it will full of holes and no free electron. Full of free electrons. Full of free holes and no free electrons. And at the conduction band, you have what do you call it? Full
Equals
of
Free electrons.
energy levels.
3 electrons.
And then with what do you call it? So so the orbital is energy level. What happens is when you when it interact with each other, each what do you call it? Each conduction band have many of the energy level like this, like billions. Okay, but the top here, the energy level is where for electron to move freely, it needs to go to the conduction band. So energy levels can only be in the conduction band or valence band using according to the Pauli exclusion principle. So that's why this gap is called the forbidden band gap. That you cannot have energy levels. And all the energy levels should be inside the conduction band and inside the valence band. Okay. So my question then, my question to you just now, can we have energy level inside the what do you call it? Inside the forbidden band gap here? The answer
Forbidden.
is for intrinsic cannot. Intrinsic cannot. So but for doping or the extrinsic semiconductor, you already put impurities. It's no longer pure. When it's no longer pure, oh, your internet connection is unstable. Can you hear me? Can you hear me?
Yes, I can hear you. Yes, I can
Yes,
hear
ma'am.
you.
Oh, I don't know why it says my connection is unstable. Okay, then what do you call it? Apa tadi? So when you dope it, what happens is you will have energy level of the donor inside the band gap. So for example, if it's a N type, what's the energy level? Is it close to conduction or valence if it's N type?
It's conduction to conduction.
Why? 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 Answer me why.
Because we have doped with an atom that has extra electrons. So it has excess electrons. That is why.
Wait a second. Satu kelas ni. Hah? Aku belum tahu. So that's class at home. Suddenly, my husband told me about something about food. I don't know. Okay, so right now where was I? So where was I? Or where were you?
Uh, if there are energy levels between in this forbidden gap.
Okay. So when you are answering why n-type is closer to the conduction band, right? Because n-type means you have free electrons, right? So in order for it to be
Yes,
free,
yes,
it has to be to the conduction band. So
yes, ma'am.
the energy level of the donor will be close to the conduction band. So this will be the energy of the donor atom, right? And then if it's a p-type,
Close to the valence band.
Yes, fellas.
if this is for n-type. If it's a p-type, it will be close to the conduction valence band receptor. Okay. Now, my next question: where's the Fermi level?
In the middle.
It is in between for intrinsic.
Here.
In the middle for intrinsic.
This now I'm drawing for the extrinsic, right?
Yes,
Yeah.
extrinsic.
But ma'am, which type extrinsic is it? P type or N
So
type?
let's say for n-type.
For N type, it will be for N type, it will be.
So it will always be in middle. So it will be in the middle
Yeah.
of the energy level of the donor to the conduction band. Allah, we
Yes,
have another 10 minutes.
Yes.
So fast. So then if it's p-type, the Fermi level is in between. It's always 50%. In between
Yes, ma'am.
middle of the energy level of the what do you call it of the acceptor atom to the valence band. So if it's intrinsic, it will be, because intrinsic is you only have the conduction and you only have the valence band, right? There's no other energy level. So for intrinsic, the Fermi level is
In
that,
between.
yes, the Fermi level is exactly in the middle. Okay. Any question?
No.
Make sure you remember. So I will stop sharing here. Let's go back to the slide. We only have 10 minutes. Okay. If it stops, I will give you another link. I don't know whether can we use the same link or no?
I don't know.
You don't know? How to do this? Okay. You don't see my slide, right? Can you see my slide?
No, ma'am.
Not now.
Share screen again. Okay. So maybe this is just recap. This class recap share. Okay, so that's, you can see it right now, right?
Yes, ma'am. We can see.
Macam mana ni? How to make it full? Let me. All right. So, can you see the whole slide, or is being blocked by your videos?
Yes,
We
ma'am.
can see the whole slide.
Little portion is blocked. Little portion.
Little portion is
A
blocked, right?
little. Yes, ma'am.
So same as mine. So how to make, how can I make it?
Ma'am, share screen with video.
I can only.
Ma'am, we can minimize the videos ourselves.
You can do?
Yeah.
Okay. So because I also cannot see part of some of the slide. Right, you manage, yeah?
You can either minimize all the webcams that we have, or you can drag it away.
Yes, you can. Okay, I can have the whole, or I can put it, or I can drag it to be the other side, right?
Yes.
Okay, good. Can I put on top or? Okay, it's okay. Right, so you have this. So we know about donors and energy levels. So if it stops, the Zoom, I will give you, I don't know when it will stop. So I will just keep on going until it stops. Then we know you need, so the donor atom will sit in between the, what do you call it, the semiconductor
Conduction.
atom. No, the atom here. So this is the semiconductor atom, and your donor will sit there inside the lattice. It will not change. The lattice, Anas, lattice constant is the distance between this and this atom. Okay, so it won't change. If you put a donor, see, the distance doesn't change. So the lattice constant doesn't change with doping.
Constant.
Okay. So what is this? I don't know. We can read this. Okay. So finish off slide number 1. Let's go to slide number 2. Slide number 2. Share. Okay. Number 2. This slide number 1 lagi. You see slide number 1, number 2? Huh?
Number 2. Slide number 2.
Okay.
Ma'am, who is having photo detector as assignment?
Sorry? No. Mobility. Okay, let's look at this. Now, ni slide nombor 2 ke 3 ni? This is not slide number 3, right?
No, mobility is number 2.
This is slide number 2.
Yes.
Okay. Okay. Oh, so we went through this, right? Okay, good. So kita dah go through, right? We went through this already, right? So what is mobility? Who want to tell me what is mobility?
it is how easily the carriers can move.
Yes. So mobility is a measure of how the carriers, the field carriers, how easy or difficult carriers to move. So so there are different factors that influence the mobility, how easy or difficult. Different material will have different mobility. So that's why if you want a faster device, you need to use different semiconductor. So the cheapest one, quite good mobility is silicon. But if you want for high end, normally for military purposes or military, they need very high end. So they might use different, expect more better mobility materials such as gallium arsenide, which is more difficult to find and more expensive. Okay, but it will be faster because the electrons and holes can move faster. It's easier to move inside the semiconductor. So there are factors that affecting the mobility, such as the temperature. So as the temperature increase, is the mobility increase or decrease?
Decrease.
Why?
Because of vibration, atoms vibrate and collisions happen, their speed decreases.
Okay. As you increase the temperature, what happens is the atom will vibrate. So when the atom vibrates, it's more difficult for the carriers to like navigate through the semiconductor. So it will hit, it will bump through the moving atom, right? And that will reduce the mobility. Okay, so in the end, so that's why you will have velocity saturation, whereby if you keep on increasing the voltage, the electron also will not keep on increasing the velocity or the speed, because it will start hitting more the atom, and this is called lattice scattering or phonon scattering. Okay, lattice scattering or phonon scattering is the same. Phonon because the heat, it will move. Okay, and lattice is also because it hitting the lattice, it hitting the atom inside the semiconductor. Okay, conductivity.
Ma'am, please
Yes.
can you repeat lattice scattering?
So lattice scattering is similar. It's the same. It's like phonon scattering. It's the same thing, except for because phonon scattering is when when you increase the temperature, you will increase the phonon, the heat, right? So the heat will actually make the lattice vibrate more, right? So that's lattice scattering. It's the same as phonon scattering, two different names.
Okay.
So if you answer in the exam, you can answer both. It's correct. Okay, you can stop me anytime for question. Less than a minute to stop. Okay, you will stop us.